first sight, the atmosphere of the Earth looks complicated, but patterns of atmospheric motion can be identified. Some of the patterns are predictable, and some are not. A band of cloud within the tropics is evidence of Hadley cells. At higher latitudes, cyclonic features can be identified. Hadley cells are caused by hot air rising at the equator, migrating polewards, and descending at higher latitudes to return at low altitude. They are more pronounced over the land, which is hotter. The west-east rotation of the Earth results in a Coriolis effect, which is manifest as a spiral motion. Friction drags this spiral open. This pattern is predictable. The Hadley cell motion extends over large distances, but at temperate latitudes is quickly dominated by turbulence. Eddies from the Hadley cell form the cyclonic features which dominate British weather. Unfortunately, cyclonic features are quite unpredictable. An extreme example of a cyclonic feature is a hurricane, which can involve the complete breakup of a Hadley cell. Hadley cells and cyclones can also be identified in the other planets of the solar system. The dominant pattern of atmospheric motion on Venus seems to be a single Hadley cell, extending from equator to pole with wind speeds greater than 200 miles per hour. Solar radiation does not readily penetrate the cloud layers, so this motion is not driven by the surface of the planet, but by temperature gradients at altitude. The Hadley cells themselves drive circulation at even higher altitude by friction. This is the movement we see in the upper atmosphere. Under high-speed east-west cloud movement, the rotation of Venus is slow. Why the wind speed is so high and in the opposite direction to the slow rotation of the planet is not known. But a contributing factor is a heating of the day side, which sets up pressure differences in the atmosphere, resulting in an east-west thermal tide. Moving out to Jupiter, atmospheric circulation can be seen in bands of cloud moving east-west around the planet. Different bands move at different speeds. An exercise is about to follow involving these cloud movements. Your video notes explain what to do. If you have not already read these, you should stop the tape and do so now. Mark the position of the ringed spot, and also mark the width of Jupiter at the same latitude. Now mark the width of Jupiter at the equator. Also note the time on the clock at the top of the screen. I'll run the sequence in a few seconds. Mark the furthest point of the dark spot and the corresponding time. Don't worry if you don't get everything at once. I'll run the sequence several times. You might like to play this sequence more than once. Now you should calculate this wind speed on Jupiter. Jupiter's atmosphere is rotating much more rapidly than that of the Earth. With this faster rotation speed, a model based on Hadley cells and an atmosphere less than 100 kilometers thick produces a banded structure. Here you can see closed rings which represent eddies produced at the boundaries of well-defined bands. cyclonic and anticyclonic features are also present. The most famous of these is the Great Red Spot, which is anticyclonic. This is a giant whirlwind surrounded by eddies. It might have persisted for centuries. Saturn has a much fainter banded structure than Jupiter. We can only see it here because the image has been enhanced. Saturn also has storms. These images show the Great White Spot, which developed over a few months and eventually encircled the planet. The white spot is cyclonic, but is not persistent like Jupiter's Great Red Spot. When Voyager flew past, there were no large-scale features on the planet. The spin axis of Uranus is heavily inclined, so although its weak banded structure appears concentric, it does follow the spin of the planet and is similar to that of Saturn and Jupiter. These bands are clearer on this enhanced still of the planet. Take the enhancement away and Uranus appears almost featureless. By contrast with Uranus, Neptune does have some clearly visible cloud movements. Here are two features seen from above the South Pole. The most notable feature is Neptune's great dark spot. There is also a feature called the scooter. Like Jupiter, these features reflect the differential motion of the bands of Neptune's atmosphere at different latitudes. But studies of Neptune have shown that the speed of the fast-moving scooter is also different to other features at the same latitude. Why might this be? Are latitude and longitude the only variable positions for an atmosphere? From Neptune right back to Venus, similar types of atmospheric circulation can be seen. Now this is most surprising. Think of the differences in sunlight that the planets experience. At the extremes, the energy flux on Neptune is only 1/1000th of that on Venus.